This video is with regards to Unit 3, which deals with discrete probability distributions. It can simply be put as probability models for numerical discrete values. So there are some important points laid out there. It says discrete probability distributions and numerical probability models for random variables, meaning a probability table, okay, for random variables. Now we have to make a distinction between what is a variable and a random variable. So a variable now is a characteristic of the object of study. And here, since it's discrete, it has finite or countable number of values. That's a variable. So a random variable now is a numerical variable whose value depends on chance. The important point here is that the variable is numerical and it can be discrete or continuous here. Now, the word random also now implies that its value depends on chance. That means there's a probability value associated with that value that it can assume. Okay, it depends on probabilities. We'll delve in that further as we move along. We will only be dealing with discrete random variables, and random variables are denoted using letters such as x, y, s, uppercase, etc. So discrete random variable can have distinct values. For example, 1, 2, 3, 4, 5, or 6. And that's it in the case of throwing a six-sided dice. Yes? So when you toss the dice, there's a probability that you may get a 1. So here you would probability, there's a chance that you may get a 1. So the value of 1 for that variable has a random nature to it. Okay, it depends on a probability value. It may or it may not happen. Okay, because you may get a 1, a 2, or 3, or 4, or 5, or 6. Okay, so that's why they call it a random variable. And it's discrete because it's countable. And another point is that a probability histogram is a bar chart in which the horizontal axis corresponds to the value of the random variable and the vertical axis represents the probability of each value of the random variable. So let's look at example 3.4. It says a discrete random variable x, well, that should be z, has the following probability distribution. So z now can only assume 1, 2, 3, 4, or 5. Nothing more, nothing less, no value different. Okay, because these are all the values represented on this table, on this distribution, or on this model. Okay, and the probability of getting each one is represented here. But what you notice now, some values are given by letter B and 2B. Okay, but a key characteristic of a probability distribution or probability model, or how you want to be called it, a probability table, is that the sum of the probabilities must equal to 1 and only 1. So 1 over 16 plus 1 over 8 plus b plus 2b plus 1 over 4 must be equal to exactly 1. So that must be taken into consideration when dealing for probability distribution. And it says here to find the value of b. That's for part A. Part B says to find p of z less than or equal to 3. C is asking for the expected value and D is asking for the variance. So let's go to the solution for A. So as you can see, use was made of the rule, if you want to put it that way, or the characteristic, the inherent characteristic of a probability model, whereby the sum of the probabilities must be equal to 1. So some fractions will convert it to decimals, 1 over 16, 1 over 8, 1 over 4, they will all convert it to decimals. And an equation was created to solve for B. One equation, one unknown, B solvable. So a little bit of algebra was employed here. And Well, these two steps are repeated. That's a little typo. However, you can see that b plus 2b is 3b, and 0.0625, 0.125, and 0.25 were added to get 0.4375, and it was subtracted from the left, subtracted on the right. So that's why it's appearing as a subtraction on the left side from 1, and 3b remained on the left. So b now is equal to 1 minus 0.4375, difference divided by 3, and which gives us a value of 0.1875. So let's go to the part B now, which says to find the probability that z is less than or equal to 3. So now we have the value of b and 2b. We can substitute and complete the probability model. And here it is. So now we can easily find p, the probability that z is less than or equal to 3. Probability of z is less than or equal to 3 is equal to p of 3 or p of 2 or p of 1. Now, although whenever you are analyzing probability questions and you mention the word or, that means you have to add. If you mention the word and, in probabilities you have to times, and in arithmetic is plus, but or in and in probabilities is times and or is plus. So that's why you have this plus here. The probability that z is equal to 3 or 2 or 1, because these are the values that are less than or equal to 3. And that these are the probability values associated with each one of them, and they're added to give 0.375. The expected value, we go to the formula for expected value. Here it is. It's actually population mean mu is the sum of x times p of x. Is the sum of the product. Not the sum of x, is the sum of the product of x times its corresponding probability value. Here you have it in this notation, or you have it in this notation. You can use mu or you can use expected value. So basically you go to find the product and then sum. Now for the variance, now you've got two formulas. You've got the sum of the difference, well, the deviation squared times the corresponding probability, or the sum of each variable squared times corresponding probability minus the mean squared. So let's see what was used. We can capture these formulas and we are written into the question. And as we know, the standard deviation is the square root of the variance. So we can capture it there one time too. As you can see, the mean was calculated by finding the product of each variable times its corresponding probabilities, and the sum was obtained, and this would have given us the mean. Here it is. 1 times 0.0625 plus 2 times 0.125 plus 3 times 0.1875, etc. And you add it, yes, 5 times 0.25, and the mean was obtained to be 3.625. Now the variance, now it appears that formula 2 that was applied, the second method. So as you can see, each values a product of the variable of the values squared. If you have values of the variable squared times its corresponding probability we will obtain, and then subtract the square of the mean. Here it is. So this is the method that was applied. And that difference between the sum of each variable squared times its probability value and the mean squared, that would have given us the variance. If the standard deviation was requested, we would have square root the variance to get the standard deviation.